Thank you. I'm glad you said that because that's a mouthful. This is some work that is a collaborative or a collective work of the LAMP team and some of my colleagues at APL. And I'd like to thank LAMP and the Lunar Science Institute for funding. So, can you please start the movie? As Alan was explaining this morning, LAMP is on the Lunar Reconnaissance Orbiter. It's a FUV spectrograph. And during the L-cross impact, we were looking out over the limb of the moon to see the vapor plume. And that shows the plume expanding and crossing our field of view. And then we crossed over the impact site and continued over the South Pole. So I just want to point out, we saw the plume here 45 seconds after impact, but we didn't cross the impact site until about 90 seconds. There was still some residual vapor there, but mostly we saw a very strongly peaked signal pass us. So what I want to do today is try to go from what we saw with LAMP to what the abundance of volatiles in the regolith is. And it's not so easy, you know, I mean, we just had this little field of view here, and we're trying to relate what we saw in here to what the abundance is in the regolith. And so, you know, how are we going to do that? Well, we'll try to do some scalings. First, we have to scale what's in the field of view of LAMP to the overall amount that was in the vapor plume that was released, and then try to relate this vapor plume to the regolith from which it was derived. And then you also have to fold in an efficiency of release because you may not release all of the volatiles from whatever portion of regolith they came in. So that's how we're going to get from A to B. So this is the spectrum that LAMP observed of the vapor plume. And we have wavelength down here going from 130 nanometers to 190 some. And we saw this very strong peak here between 180 and 190 nanometers. And Randy Gladstone has done a fit of this spectrum and fit this peak by a combination of mercury, this green line here, calcium, this blue hump and this other blue hump here, and magnesium here. These molecular lines over here, Randy fit by a combination of molecular hydrogen and carbon monoxide. And if you just look at the column abundances that were observed and you add up how much mass that relates to, or that is, we see, you know, under a kilogram of most of the species and, you know, just over a kilogram of the H2 that was in our field of view. So then, now to relate that to the expanding vapor plume, you know, the vapor was expanding past LRO while LRO was flying across it, so we have the relative velocity to consider. So what we do is we model the vapor plume with a Monte Carlo model, and then we fold in LAMP's field of view to see what the time series would look like as LAMP traveled across the impact site. And when we do that, we get the best fit to the time series, which we added separately the time series for the 180 to 190 nanometer feature, which was the mercury, calcium, magnesium. And that one up here, the black lines are the data. And then we have magnesium, calcium, and mercury, and you add them up together and you get this red line. And that came from, to get the timing of the peak correctly, it came with a simulation that used a bulk expansion velocity of 3.5 to 4 kilometers a second. And the temperature was relatively unconstrained. We could use a large variety of temperatures and get similar fits. However, for this curve, which was the 130 to 165 nanometers. In this case, it's the red bars that are the data. If you look at the H2 simulations and the carbon monoxide simulations, and you add them together to this combined light curve, this best fit came when we used a bulk velocity between 2.5 and 3.5 kilometers a second. And the temperatures were more constrained for this, where the best fit came with temperatures between 500 and 1200 Kelvin. So then when you fold in both the time series and the spectrum, we used the model to estimate how much mass was in the vapor plume in order to get this amount in our field of view as our field of view, or to match that fit to the column abundance. And so we got about 117 kilograms of H2 was needed to be released in total in order for LAMP to have observed 1.33 kilograms. And 40 kilograms of carbon monoxide, 16 calcium, 4 of magnesium, and 12 mercury. So now here's a exercise in moving the decimal point, which I'm sure you guys can do as well as I can, and probably even better. But so just how much regolith, if you want to know what the abundance is in the regolith, then you have to know what regolith it came out of. So if 117 kilograms of H2 were released, and it was released out of 1,000 kilograms, it was 11% H2. So pick your favorite. Just to relate this to what sort of size or volumes you're talking about with these masses, what I did was I said, if you assume that the density is 1.8 grams per centimeter cubed, how big is the cube that corresponds to that mass? And those values are up here just for reference. And so to get 1 million kilograms, you're not talking about that big, it's just 8 meters on a side. So now some values of masses that are associated with the actual crater and cratering. If you take the size of the crater and you fill it back in with, or estimated by Pete Schultz et al., and you fill it back in with regolith, that's 1.8 grams per centimeter cubed, you're talking about 1 million kilograms of material. The estimates of the mass that actually made it up high enough in the air to reach sunlight was a few thousand kilograms. Or if you look at the definer results, that estimated the amount of mass that was heated to 950 degrees Kelvin, it was right around 1,000 kilograms. So what mass of the regolith, are we really talking about? Which one of those is the right one to use? Well, it's actually going to depend on the volatility of the volatile that's released. And for these 5 species, they have very different volatilities. And now I've ordered our species that LAMP observed by relative volatility, where I'm showing the heat or vaporization is going up and the temperature at which you would expect a 1 bar vapor pressure going up as you go down in the plot. And the mass that was released is mostly sorted by relative volatility, which is good news, because you'd expect the higher volatile or more volatile things to be more readily released. But it doesn't matter how high your volatility is, if you only have 1 gram of it there, that's all that can get released. So you have to also consider the stoichiometry. So now we get to a circular argument, because I don't do the models of actual crater formation and what goes into that. And hopefully there are people out there who are doing that, and because that's very important information for this problem. But instead of calling this a circular argument, we're just going to say it's a sanity check, where I'm going to look at what we would expect to be the abundance of these materials in the permanently shadowed regions, and see what mass of regolith you would have to release the 117 kilograms of H2 out of, for example, to match the predicted abundance. So, and then again, I have here for reference kind of the crater parameters. So calcium, magnesium, they're refractories, and I don't think that there's a reason to expect that they would have much higher abundance in the permanently shadowed regions. In fact, perhaps you would expect a lower abundance there because they may be diluted by the presence of other volatiles. So what I did was I looked at the measured abundances of calcium and magnesium from Apollo 16 samples, and got 11% calcium and 3% magnesium, and to get the masses released that the model suggests was released, they had to come out of about 100 kilograms of regolith if they were completely volatilized and lost, or they could be incompletely volatilized and stem from a larger mass of regolith. And so that seems like it's consistent with I think both things are consistent, the predicted amount and the amount that we saw released, because it takes a lot to kick off calcium, magnesium, and if there were only 270 kilograms heated to 950 K, you have to get even hotter to kick these out. So I think that makes sense. Now, moving on to mercury. Mercury is more volatile. You only need to reach a couple hundred Kelvin to start losing a lot of mercury. And so, looking again at this number here, we don't have to get up to 950 K, so there's going to be a larger mass of the crater, or within the crater forming region, that reaches a few hundred Kelvin. So we're going to associate the mercury with about 4,000 to 5,000 kilograms of regolith, and say that the prediction of Reed from 99 was pretty good. Now moving to H2 and CO, the predicted abundances are much lower, and so they would have to come out of a lot more mass of regolith, and we're talking about 100,000 kilograms. And I don't think it's unreasonable to get up to 1 million kilograms of regolith. So to summarize, we've related the volatiles that were in the field of view of LAMP to the overall amount of volatiles released in the plume through our Monte Carlo model, and then we try to relate that to the mass of regolith from which they were derived. And the carbon monoxide and H2, they're so highly volatile that just shaking the regolith, the friction of grain against grain, could be enough to release them. And so their source regolith is probably 100,000 to 1 million kilograms. You need slightly higher temperatures to liberate the mercury, so it probably came from about 5,000 kilograms. And the magnesium and calcium probably exist in Cabeus, similar to Apollo soils. So I'm going to leave this chart up with numbers while I take questions.
Thank you, Dana. All right, we have time for one question. Dale Cruikshank in the front row.
I'm trying to get a feel for which of these molecules, in particular H2 and CO, were actually detected reliably, or to what degree they're just really needed to sort of fill in the continuum in the spectrum. Is H2, for example, really there in the spectrum?
I believe it is. I think, their molecular lines are, oh, wait, where'd it go? Okay, sorry. Oh, there it is. Molecular lines vary depending on the rotational vibrational temperature. So there are a lot of free parameters in fitting those. However, I don't see how we could make all of that without there being some
Okay.
molecular constituents there.
Thank you.